All right, so in this video, we'll be looking at different sets in the complex plane. So far in this course, we've been looking at the algebra behind complex numbers. This time around, since we can express complex numbers as vectors, we're going to be looking at the calculus behind complex functions, and these will involve using sets in the complex plane. So we're going to examine the functions in the complex plane. Okay. All right. And very soon we're going to apply calculus to these functions. Okay. Since these sets are vectors in 2D space, we can look at some sets in the complex plane. So before we do that, we're going to state some sets. In the complex plane. Some various ones. Okay, so the first we'll be dealing with quite a lot are circles in the complex plane. And it's notated like this: z minus z naught is equal to rho. Okay, so and this also equals to the square root of x minus x 0 plus y minus y 0. Both of these are quantities squared, and this equals to rho, right? Okay, this is for any complex number. Z equals x plus iy, and a fixed complex number z naught at 0 plus I times y 0. So essentially it's the distance formula, right? X minus x naught squared plus y minus y naught squared equals to rho. So the center of the circle is going to be, I'll say a coordinate x0, y0, and the radius of the circle is rho. Okay, so geometrically, we are looking at the boundary of the circle with center z naught and we're fixing a point on the boundary, and this is the radius rho. Okay, so this is the illustration. Okay, so for example, how do you define this? Well, if you said unit circle, you're right. The center is at the origin, right? The center is at the origin, and the radius is 1. So this is how you would define the unit circle in the complex plane. So I'm going to denote the set of complex numbers as this blackboard letter C with a bar in the middle, right? So that's the set of complex numbers. How about this one? Z minus 1 plus 3i equals 5. Well, we want to write out the equation of a circle like this. right? Z minus Z naught equals to rho. So if I write out this quantity as the absolute value of Z minus, if I factor out the minus sign, 1 minus 3i, then we'll have it in the right form, okay? In the right form. So this is a circle with radius 5, and the center is at 1 plus 3i. 1 plus 3i, or just the 0.13 in the complex plane, right? In the complex plane. So there's going to be other sets that we will deal with when presenting complex functions. Mainly, we're going to be looking at what are called open sets in a complex plane. So let's look at some different definitions, and we'll build up to the definition of an open set. So a point in the complex plane, let's say Z naught, is what's called an interior point, of a set S in the complex plane if there exists some neighborhood of Z naught that lies entirely in S. Okay. That's what's called an interior point. Okay. And what is a neighborhood? A neighborhood of Z naught is a circle with a fixed radius with center Z naught. So this is a neighborhood of Z naught. Okay. So this is the definition. So we're looking at the points that are on the boundary of the circle and let me denote this a different color, rho, and we want the points that are on the boundary and the interior of the circle. So there'll be those points there, okay? So on the boundary and the interior of the circle, okay? So that's what's called a neighborhood of Z naught, okay? And this is where we're going to build off on defining an open set. If every point in S, so S is a subset of the complex plane, is an interior point, then S is an open set. Okay. And that's what it means to be an open set. So let's actually look at an example of an open set. So for example, if I let S be the points Z inside the complex plane, such that the real part of Z is greater than 1. Okay, this is a set. So this on the right side of the vertical bar means what elements are in the set. The right-hand side of this vertical bar is the condition of the set. This is how you write out set notation. Okay. Should all know at this point, right? So S is the set of all complex numbers such that the real component of a complex number Z is greater than 1. So graphically, it's represented like this. So here's the real part, and then the imaginary part is here. So we want the real part of Z being greater than 1. So it's going to be just a vertical line that's down, and we want these points to the right. Okay. So typically, if you have a set that doesn't include a boundary line or a boundary of a set, you'll be dealing with an open set. Okay. So for example, if I were to pick a point that's super close to the boundary, let's say at so in this case it's let me do it in a different color, 1.1 plus 2i, right? Let's say this here. In order for this to be open, we need to find a radius, a circle, I should say, which contains points that are entirely in S, which are entirely on the right-hand side of this set. So if I pick rho, my radius equal to 0.05, that would be a small enough radius. So in order to contain all the points that are in S, okay? So if I were to zoom in this part, right, you're going to have the line here, and then the center, right, 1.1 and then 2, and then 0.05 is a small number, a really small number, right? So if I do this cross method, if I add 0.05 to the left and to the right, and then 0.5 up and down, we'll get a circle, right? So this is 1.1, 2.05, and 1.1, 1.95, right? 1.152, and 0.95, 0.95, and 2. Okay, so this is our circle, right? And if we zoom in here, we will contain points that are in S. Okay, so in this case, this would be an open set. Okay. So the trick here is, if you look at sets that do include boundaries or not, it's a good indication that you may have an open set, right? So some quick examples of a set that's not open could be something like this. So the exact same set, but this time we will be including boundary. So the real part of Z is 1. So here's the real part of the Z axis and the imaginary axis is here. Okay. And then let's say S would be the set that is so the real part of Z is greater than or equal to 1, right? This case, this will not be an open set because if I were to take a point that's on the boundary, just any point on the boundary, let's say 1, 3, if I were to choose any radius of a circle, well, the good news is we'll have points that are in the set, but the bad news is we'll have points that are not in the set. It's like these points over here. That's bad news. An open set implies we want to find a radius, so we contain points, every point in that circle. It has to belong in the original set. Okay. This is not an open set because we have points that are in the set, but we have points that are not in the set. Okay. So this is not an open set. So it's not open set. Okay. Let's see, part B. How about this one? And let's say S is defined here as the set of all complex numbers such that the modulus of Z is bigger than 1. Okay. Right. So S would be the complex numbers, which the modulus of Z, the length, is greater than 1. Okay. So right here, the dashed lines indicates the unit circle. Z equals 1. Okay. So in this case, this would be an open set. Right? So this is an open set. We are not including the boundary of the unit circle. Okay. This one is an example of an open set. Actually, this here is an example of an open set. Oh, this epsilon means is an element of such that the imaginary component of Z is negative. So we're looking at these points down here. So we're not including so we're not including the real axis in this case, right? So this here is also another example of an open set, right? And then finally, let's say something like this. Okay. We have some sort of a shell, but it's not including the boundary of the shell. So this would be the circle. Z equals 2, and then Z equals 1, and we're looking at the points that are inside this shell, right? This here, so if I look at the set S, and this is the set of all complex numbers, Z, such that Z is in between 1 and 2. This here is also an open set. We're not including the points on the boundary. So this here is also an open set. Okay. Now, caution, right? A set that is not open does not mean a set is closed. We'll go over a closed set in a second, okay? But so that's the caution, right? A set that's not open does not mean that it's closed, okay? You may have a set that looks like the what's called this. So this particular shape is what's called an annulus. Okay, the mathematical term. But you could have an annulus that looks like this, right? We could have one annulus where one boundary is not included, but we'll have another boundary that is included, right? That is included. So and this is the mathematical definition of this set here, right? And well, all the points in here. So this set is an example of both an open and a closed set. So spoiler alert, a set is closed if you'll deal with a set that's closed if it contains the boundary of a set. Okay. So we have the boundary that's included on the circle modulus of z equals to 2, right? So and the set does not include the boundary of the circle modulus of z equals to 1, right? So this is a set that's both open and closed. Okay. So that's just an example of open and closed sets. So let's actually talk about what's called the domain of a complex set. Okay. Some terminology that you should write down is this. So if any points Z1 and Z2 in a set S can be connected, by a line consisting of finite line segments, then S is called a connected set. Okay. So if I have, let's say, a set that looks like this. So here's S, right? And if I have 2 points in this set, Z1 and then Z2 is over here, right? I can connect Z1 and Z2 by following these line segments, right? It's just constructing line segments so you can connect Z1 to Z2 in some way. If you have that, it's called it's called a connected set, right? And also an open connected set is called a domain. Okay, it's called the domain. All right. And then and we'll go over some more terminology. Yeah, this section is just writing out different definitions of things. And we'll go in the next chapter where it gets really fascinating. So let's talk about what a region is. So a region, a region is a domain in the complex plane with all, some, or none of its boundary points. Okay. And a set containing all boundary points is called a closed set. So in other words, so just remember this, not closed does not imply set is open. Okay. So don't fall in that trap. So for example, a closed disk. A closed disk is an example of a closed set. So this is what's called a closed disk with center Z naught and the radius is rho. And we're including all the points that are in the interior and the boundary points, right? The interior and the boundary points. So that's a closed set. If there's another thing to point out, if the center is deleted from either an open or a closed disk, they are called a punctured disk. Okay. All right. So the last couple of definitions is what's called a bounded set. A set S, this is what's called a subset. So this is a subset of the complex plane, right? So if a set S is a subset of the complex plane, is bounded if there exists a real number R greater than 0, such that modulus of Z is less than R, for every Z in S. Okay. A set S is unbounded if S is not bounded. So this one is logically sound, right? Okay. And I want you to write out, I want you to work on these comprehension problems. So page 31, 2, 4, 8, 12, 17, 18, 20, 22, 23, and 30. Okay. This is a hefty definition version of this video. So we're going to be looking at different variations of sets in the complex plane, because these will be very important when we are doing calculus in the complex plane. So it's good to note about what an open set is, what a closed set is, what a bounded set is, right? All those types of topology in the complex plane. So in the next section, we'll go over functions in the complex plane. So thank you for watching, and I'll see you soon.